This is our third installment of How Science Works. In this lecture, we'll address data collection and making conclusions from our data. Here are your learning objectives. This is the third time we've seen this definition of science. In the first How Science Works mini lecture, we talked about what questions we can ask in the field of science. In the second How Science Works mini lecture, we looked at the different approaches used in science. And in this mini lecture, we'll look at how we determine the answers to our questions. When we collect data, we must always work within certain limitations. We had limits as to what questions we could ask, and we have limits to what research designs we can use. Those limits end up restricting what data we can collect. We could also be limited by funding, the technology to access or measure our samples, the amount of time we have, or the access to our samples if we're researching, for example, endangered species or a deep sea ecosystem or humans. We cannot do whatever we want to our research subjects. We have ethical limitations. While we tend to think of limitations as a bad thing, they can actually be a very good thing. Of course, ethical limitations are a very good thing, but any limitation allows us to think creatively to figure out a way to answer our question while working within these limits. When we collect data, we always want to be as accurate as we can in measuring or recording those measurements and in processing those data. Sometimes our data will show outliers, like in this example. Most of our sample follows this trend, but then there's this one outlier way up here. Sometimes outliers indicate an error in measurement or recording of the data. We always want to check them. If we have an error in a measurement down here, that is something we want to correct, but it's not very influential to our conclusions. This outlier would actually influence the trend line of these data down here, pulling the line upwards. The other reason to always check the outliers is that they can be the most interesting. This individual may have a trait that is very unique and might be more interesting than all these individuals down here. An incident like this occurred with a Duke researcher a few years back. He was researching cancer and had to inject lab rats with a chemical to give them cancer. Most did develop cancer, but a few did not. That became much more interesting than his original research question, and he ended up switching his research to study these outliers. When you collect data, you always want to revisit your question to make sure you're measuring what you are supposed to measure. Let's look again at this study we covered in How Science Works Part 1. If we were conducting a study to see if night owls are more intelligent than early birds, we would want to know two things. What time people get up in the morning to determine if they're a night owl or an early bird, and we would want to measure each person's intelligence. In this study, it seems people were asked what time they get up in the morning. But it's kind of weird because it looks like everybody in the study woke up between 10 and 11 in the morning. To me, that's not an early bird at all. I would probably categorize people as those who wake up before 6 a.m. and those who wake up after 10 a.m. Then I would run a series of intelligence tests to measure IQ. This researcher, though, just collected the people's childhood IQs. The problem is that IQ changes over time. It's a comparison amongst your peers. If you have an IQ of 100, you have average intelligence. But if you continue to challenge your brain and to learn more information and more skills throughout your life, and your peers don't, your intelligence will increase compared to your peers. Measuring childhood IQ to answer a question about adults doesn't work. There are many possible errors that can arise during data collection. Some of these errors might be mistakes that are just unintentional, but some might be biased, which are intentional errors. The last study with the night owls and early bird intelligence had incredibly bad research design. Poor research design results in poor data. Sometimes data are falsified. If this is found out, the researcher will usually be banned from ever receiving funding again. Basically, they lose their entire career. Omitting data could be intentional or unintentional. And sometimes, if it's intentional, it's not necessarily for nefarious reasons. There are some very good reasons to omit data. It just has to be clearly addressed and logically explained. And sometimes there are unintentional errors in the data because someone misread a measurement, mistyped the data, or because the recording equipment is malfunctioning. Let's look at a data collection error addressed in a 2016 study published in the British Medical Journal. The authors used death records to estimate the number of deaths in the U.S. due to medical errors. This estimate showed that medical errors were the number 3 cause of death in the U.S. The researchers of this study had to estimate these deaths, though, because in the U.S. there is no entry option on a death certificate for medical errors. The authors of this study were pointing out that there's an error in data collection for cause of death, and that it's incredibly important these causes of death be recorded so that we can address the problem. What type of an error in data collection would this article be pointing out? This would be omitted data. We're simply not collecting these data points. Let's revisit this urination law study again, and the data that one of my classes submitted. We'll especially focus on these 2 data points up here that were both 120 seconds. These are outliers and substantially shift the average upward. What do you think we should do with them? Should we get rid of them or average them in? All these data points were anonymously collected and self-reported, so I have no way of checking to see if these people actually peed for 2 solid minutes. I kind of doubt it, though. For one thing, both entries had exactly 120 seconds listed. I feel like someone might say, wow, that pee was like 2 minutes long, without actually measuring the time. Or since the students could submit multiple entries, one student may have submitted the same data twice. So I think you could make a good argument for removing these 2 outliers. However, it brings up more questions, like the lowest pee time was 2 seconds. Did that person mistype? Did they actually time a 2-second urination event? If we average in the 2 120-second times, it significantly changes the average pee time. The median, or most common entry, was 12 seconds. But by averaging in these really high numbers, it shifts the average up to 17 seconds. That's a 40% shift in time. There are other options, though. We could keep these data points in, but then just use the median time instead of the average. Let's talk about different types of data now. There's qualitative data and quantitative data. Qualitative refers to the qualities of a variable. These are things like categories or descriptions. Quantitative data refers to quantities. In both of these examples, the data collected relate to visualizations. In one study, The data are the drawing qualities of these children. In this other study, it's a count of the number of mitochondria in a cross-section of a cell drawing. Even though both of these data relate to drawings, one is qualitative data and the other is quantitative. I'll have a link posted on Moodle for an activity to practice identifying data as qualitative or quantitative. We can also have direct and indirect measurements. A direct measurement is measuring the variable you're actually interested in. If you're interested in plant growth, you could measure the height of a plant. If you're studying the impact of diet on diabetes, you could measure blood sugar levels. Indirect measurements are often used when it's too difficult to directly measure what you're interested in. For example, if you test out different antibacterial cleaners, it's really difficult to measure the number of bacteria left. They're just too small and generally too many. But we can use a measurement of light instead. If we transmit light through a clear fluid and measure the amount of light that comes out the other side, it should be close to 100%. But if we have a lot of bacteria inside that fluid, they will block the light. So the lower the amount of light that gets through, the more bacteria you have. We're measuring light, but it's indicating the amount of bacteria. This type of indirect measurement relies on logic. What kind? Deductive, inductive, or abductive? This would use deductive logic. Light travels through a clear liquid. Bacteria suspended in a liquid will block light from traveling through. Therefore, more bacteria present in the liquid will block more light. Let's look at a couple other examples. If we're interested in how many sea turtle eggs there are deposited on a certain stretch of beach, we could go around and try to locate all the nests and count up how many eggs there are. More commonly, though, researchers travel down the beach early in the morning and count the number of turtle crawls. These are the marks in the sand made by the female sea turtle as she traveled across the beach to lay her eggs. We know that the average number of eggs in a nest is about 100. So if we find 5 turtle crawls, we can estimate that there are 500 eggs. We don't have to disturb the nest, and this type of monitoring is very quick and very easy. You probably use indirect measurement all the time when you're searching around parking lots. Sometimes you'll be in a full parking lot looking for a space, and there's a large SUV that blocks your vision of the next spot. You could slow down, edging up to see if there's a car occupying that spot, or you could use an indirect data collection approach to determine the same thing. You could look for shadows. We know that vehicles produce shadows, so if you can see the shadow of a car, you know that that space is occupied.